Hello, welcome back. So as you can see today, we're doing things a little differently. Today, instead of learning this lesson at the whiteboard, we're going to learn it on my computer screen, which I have put on your monitor for you on the video feed. So we're at the computer instead of the whiteboard, and this is both for a change of scenery and also because this lesson involves various pictures that I need to show you. And these pictures are a little detailed, so I've decided that it would be easier to just show you the pictures on the computer than trying to draw them on the whiteboard. You see, today we're moving into an interesting lesson. We're going to learn about electrical wiring diagrams, hence the need for our detailed images. So what are electrical wiring diagrams? Well, when you're an engineer or if you're building a circuit for whatever reason, when you're building an electrical circuit, you need a diagram in order to tell you how to connect all the components together on the circuit board. And this is what an electrical wiring diagram is for. It's a diagram that tells you how to wire all these components together. So each electrical component is represented by a symbol, and we call these schematic symbols. So by using schematic symbols and connecting them with lines, which you'll see in a minute, electrical circuit schematic diagrams tell us the way that components are interconnected with each other. So one thing you do need to know about these electrical diagrams, the physical appearance of these components, like how they look in real life, and the length of the wires on the circuit, they're not really accurately represented in these electrical diagrams. But that's okay because they don't really matter. Because if you think about it, a circuit will work no matter how long or short the wires are, as long as the components are connected. And as long as the components are the right ones that you need, it doesn't really matter as much how they will look. So now let's look at a sample schematic diagram. This is it over here, figure T-3, figure T3. This is a sample schematic diagram. So if you see these little things here, they're numbered. See, number 1, these little diagrams here, number 2, number 3, number 4. This one's not numbered, but it's still something. These are the electrical components. And these lines represent the wires that all connect these components together. Alright, so these are electrical components, and you might actually see this exact same diagram on your technician class test, so we're going to study it a little more. In fact, the exam might ask you some questions about what some of the components represented by these symbols are. So especially they're going to ask you about component number 3 and component number 4. Let's look at those. So component 3, this weird squiggly thing with a weird line attached to it. Is this component, oops, that's a typo. Alright, component 3 is a variable. Component 3 is a variable inductor. It's a variable inductor. Okay, so why is it called a variable inductor? So if you see this sort of bouncy line over here, it's sort of squiggly. It almost looks like a coil. That bouncy line means inductor. So if you remember, we learned about inductors. Inductors are made out of coils of wire. And if you look at this, this does look like a coil of wire. So we know it's an inductor. But what is a variable inductor? So a variable inductor, I don't know what's wrong with that 3. Whoop. Okay. A variable inductor is basically an inductor that can sort of change how much inductance it has. So see this line here? This line means that it's a variable inductor. That's the variable part. Because it plugs into one of these points on these sort of little hump lines. So it's attached to this one right now, but it can also plug into that one or that one or that one or that one. And then that's why it's variable, and that sort of changes the inductance or something. So that's why it's called a variable inductor. So now let's look over at component 4. Now component 4 is the antenna, and this should be pretty obvious. Well, maybe not obvious at first, but if you look closely at it, it sort of looks like an antenna. I mean, it's pointing up and it's pointing sort of out in 3 directions. It looks kind of like an antenna. So those are the only components that the test is going to ask you about as far as this diagram is concerned. So that's all we're going to look at for now. Let's move on to another diagram though and learn some more electrical components. Okay, so this is figure T-1 down here. So let's look at a few of these components. Component 1 over here, component 1 is a resistor. It's this weird squiggly line over here. So if you think about it, it will actually make sense why this is a resistor. Remember we talked about how electricity often behaves like river flowing down a stream? Think about for a minute, imagine that this isn't an electrical wire or anything, but it's a river, and the river actually has to go through all these squiggly bends in the river, or the water has to go through these squiggly bends in the river. If this was a real river, then all the squiggles here, they might slow down and resist the current a little, right? And the water would flow through them slower because it would have to turn so much. So think about it that way. The squiggles resist the current. They resist the current, hence the word resistor. That's why you know it's a resistor, except instead of resisting water, it resists electrical current. Now this actually isn't an accurate representation of a resistor. A resistor doesn't exactly slow signals down by forcing them to go in squiggly lines, but you get the idea. This can help you remember that this is the symbol for a resistor on the exam. So component number 2, which is this big thing over here, component 2 is a transistor. And the way you can remember it's a transistor is because, again, you can know it has 3 electrodes. So if you look here, this is a resistor that has 2 electrodes. It connects to the circuit here and here. But the transistor connects here, here, and here. 1, 2, 3. 3 electrodes. Now, specifically, this is an NPN transistor. Remember, we talked about there are different kinds of transistors. This is an NPN transistor. So how can you tell this is an NPN transistor? Well, there's a special trick for this. Notice this little arrow on the transistor here. The arrow is not pointing in. It's pointing out and away from the transistor. It's not pointing in. Not pointing in. If you take the letters from these words, you get NPN. And yes, I know that the word in is the wrong letter, but still, you get the word letters NPN, which can help you remember it's an NPN transistor because it's not pointing in. So an NPN transistor's job is to control the flow of the current that goes through the circuit, and that's exactly what this transistor is doing here. Okay, component number 3 over here. Component 3 is a lamp, like it's a light bulb or something. This is pretty obvious. It looks sort of like a light bulb. It looks like a lamp. And component 4, these 4 lines over here of varying length, this is a battery, and that's what's powering the whole circuit. Okay, so let's look at one more diagram before we move on. One last diagram. This is figure T-2. So first let's look at component 3. Component 3 is what we call a single pole, single throw switch. And that's quite a mouthful, but I have it written here. Single pole, single throw switch. What is a single pole, single throw switch? Oh my goodness. Well, if you look at it, you can probably tell it's a switch. It looks sort of like a light switch. You can see how right now the switch is open. It's not letting electricity flow through because the circuit's not connected. But if that line here was connected to this dot, the switch would be what we call closed, or in other words, the switch would be in the on position, whereas right now it's off. And if it's on, then the current will be able to flow through, everything will be connected. So we know this is a switch, that much is obvious. But what's a single post, single throw switch? Well, if you look at it, this switch has one pole. So when we're talking about switches, a pole refers to this little line here. The line that's part of the switch, you see there's one line that goes this way on the switch, that's a pole. There's only one pole, so it's a single pole switch. And it's a single throw switch because you can only throw it open or closed one way. It either latches, it latches on here, and it either goes like that or like that. Open, closed, off, or on. So it only throws one way. Other switches might throw 2 ways. So you can flip it like this and like that, and like that and like that. This switch doesn't do that. So it's a single throw switch. Single pole, single throw switch. Alright, component number 4 over here. This one looks really interesting, doesn't it? This is a transformer. So a transformer, this one sort of changes the voltage in the circuit. So what happens is, I believe this is the electrical outlet. As the electricity goes in, the voltage will actually go from the left of the transformer, and it will move all the way to the right. And you can see here there's a number of turns here. It almost looks like an inductor, except it's not an inductor. But the number of turns will actually determine the new voltage, which is interesting. But I won't go into details. Okay, component 6 over here is a capacitor. So there are 2 ways you can remember this as a capacitor. Look at this sort of this line going like sort of that way. Like it sort of looks like an upside down C, doesn't it? That can remind you of capacitor. But also remember, if you were listening really closely, you might remember that a capacitor is made out of 2 layers of material. 2 layers, one on the bottom, one on the top, and then there's an insulator in the middle. If you look at this, there are 2 sort of parallel layers. So that also reminds you that it's a capacitor because of these 2 layers. Component 8 over here, this is a light emitting diode, or LED. This is the same type of light that's used to power the light that on your power button on your laptop computer or your computer. So it's an LED, a light emitting diode. And these 2 arrows here that are kind of going out of the diode, that represents light leaving the diode. That's how you can remember it's a light emitting diode. It's a little light. Not really a light bulb, but an LED. And finally, component 9. This should look a little familiar. We just learned that this squiggly thing is a resistor, okay? But this resistor looks a little different. It has this weird line over here that goes and attaches here. So this turns out is a variable resistor. See, this line might look familiar. We saw it just a second ago with the variable inductor. So remember, the variable inductor had the same type of line, and now we see it over here. So this must be a variable resistor that you can change the amount of resistance that it receives. Alright, so that's all you need to know for schematic diagrams, and now we're going to move into another thing that you'll need to know, and I have some bad news for you. More math. math. Sorry, we are going to look at a little bit more math, but this is, again, it's easy math. So specifically, it's not actually really math. I should have put frequency conversion. So what we're going to be learning is how to convert. Remember when we talked about frequencies and how they're measured in hertz, but there are also megahertz and kilohertz. There are these prefixes that we can put on hertz. So a megahertz represents 1 million hertz, a kilohertz represents 1,000 hertz, things like that. So these are prefixes. We put them for the word hertz, and kilo means 1,000, mega means 1 million, and giga means 1 billion. So in other words, if I say I have 1 kilohertz, that prefix kilo means 1,000 hertz, 1 megahertz is 1 million hertz, etc., etc. And we can use these to represent giant values of hertz in smaller numbers so that we don't have to write out like 9 digits of hertz when we're talking about big frequencies. Okay, and of course this also means that 1,000 kilohertz is 1 megahertz. There are 1,000 kilohertz in a megahertz. There are 1,000 megahertz in a gigahertz, etc., etc. All right, kilohertz, megahertz, and gigahertz. So then 2425 megahertz is 2.425 gigahertz. These are the same exact frequencies, just represented in different units, megahertz versus gigahertz. And this is also 242,500 kilohertz and 242,500,000 hertz. And you can see if we represent this in thousands, it'll be 242,500 kilohertz. This is also 2,425,000 hertz, which is why we have this up here. You can see how all this would work. All right, so these are, if these are a little hard for you to understand right now, the best way to get the hang of these is to practice a lot. So I have a homework assignment for you. You're going to do a bunch of problems involving converted kilohertz and megahertz and gigahertz, and it's not going to be graded, so you don't have to worry about that. All you have to worry about is how to learn all this. So you'll have plenty of practice after this lesson. So kilohertz, megahertz, and gigahertz, but there are other prefixes as well, which are slightly different. So there's the milli, micro, and pico prefixes, which you'll also have to know for the test. And these are a little more difficult because they go the other way, sort of. Whereas, instead of representing 1,000 hertz, for example, 1 kilohertz is 1,000 hertz, take a look at a millihertz. So a millihertz is 1/1000th of a hertz. 1/1000th of a hertz. You probably remember this in math. Meaning 1,000 millivolts, say, is 1 volt, or 1,000 millihertz represents 1 hertz. 1,000 millihertz is 1 hertz. So milli is sort of, when you convert something to millihertz, it sort of multiplies it by 10 to the negative third power. 10 to the negative third power. It moves the decimal point 3 places backwards, so toward the right. So micro is 10 to the negative 6 power. It moves 6 places to the left. Pico moves the decimal point 12 places to the right. Yes, to the right. Sorry, not to the left. Micro, all of these, you move it to the right. Pico moves it 12 places to the right. So this number of picoamps, say, equals 1 amp. So it's sort of similar, though. But don't worry, we can make this a little easier. So to convert megahertz, kilohertz, or gigahertz into the base unit, what we call of hertz, hertz is the base unit, the basic unit that we're dealing with. What you do is you just have to move the decimal place a certain number of places to the right. And to convert the other way, to convert hertz into gigahertz or kilohertz or megahertz, you will always move the decimal place to the left. And how much you move it depends on what prefixes is. So if you're going from hertz to kilohertz, there will be 3 places to the left. Hertz to megahertz would be 6 places, etc., etc. And similarly, to convert milliamps to amps, say, what you do is move the decimal place to the left 3 times. Because remember, milli is 10 to the negative third power, so that number 3 indicates we have to move the decimal place 3 times. And to convert amps to milliamps, you would move the decimal place to the right 3 times. Again, 10 to the negative third. Alright, so there's a handy trick that can really help you with all these unit conversion problems. So if this is really confusing for you, hopefully it's not too bad, but if it is difficult for you to understand right now, it is sort of hard to comprehend. But there's a handy trick that can help you. Try first converting everything into the base unit. Like if you're working with frequencies, convert everything to hertz first, and then convert to what the test wants. So, and if you're not working with frequency, it still applies. If you're working with amps, say, or milliamps, try first converting to amps and then convert to the unit they want, such as picoamps. So for example, if the test gives you a number in microfarads, and they want it in picofarads, you don't have to go right from microfarads to picofarads if that's too hard. First, convert microfarads to farads. You sort of split this into 2 steps. Step 1, convert microfarads to farads. So you would move the decimal place to the right 6 times, because micro is that 10 to the negative 6th power, 6 meaning move the decimal place 6 times. Then you get farads, but they want picofarads, but that's okay. Then just convert farads to picofarads by moving the decimal place to the left 12 times. And you will have a pencil and paper with you on the test, so you will be able to move and count all the decimal places this way. So again, this can be very difficult if you don't have the hang of it. So do the homework assignment, practice some homework problems in order to get a feel for these types of questions, and then you should become comfortable with that after doing those. And you can also consult the Gordon West manual and read the explanations in the book if you need to after you try the questions once. After you make an attempt, try to do it on your own the first time. If you fail after that, just try to look at the explanation and try to solve the problem. Again, this isn't graded, you're not even turning anything in. So this is just for practice, so you get the hang of this kind of problems. And study the Gordon West manual for help if needed. And there will be a mini quiz for this section. There will be a little quiz, not a mini quiz. There will be a quiz on schematic diagrams, but only homework problems for the math. So definitely study the schematic diagrams and memorize the symbols that we learned about. Alright, so that's it for this section on Picture This Part 1. Tomorrow we're going to move back to the whiteboard and learn the rest of this section, but until then, I will see you later.